Men are equal to 100 watt. They call it now Edison light bulb. So it's the first light bulb. Men, 100 watt. Ladies or women are 105. So ladies, you produce 5% more heat. That's how basically it works. I don't know why, but that's what it is.
As role models for future generations, we're building a world where wisdom and consciousness rise, harmonizing life with nature and all species. Join us. Together, let's create a balanced, sustainable future for all.
I would love to hear what you're doing with Termobuild and where you are on the journey, and to share anything you might want to.
I used to have a consulting company that specialized in buildings, everything that goes inside of the buildings, like with heating, cooling, ventilation, fire protection, lighting, security, and so on and so forth. What happened is we've been doing quite a few buildings for large corporations, private builders, developers, from large corporations were from United States, from Canada, from Europe, even from Japan. We had some clients, but I stopped doing that and I started to drive integrated solutions. What was the reason is that I realized that we as engineers are trained to support manufactured solutions. And the manufacturers usually provide the software to decide how much you have to put in the building. And usually, once we started driving integrated solutions, and I'll explain exactly what we're doing, I realized that we need only half of it to do a better job. So now, I've been doing it for 15 years, and being in the consulting industry and doing a lot of projects, we've done millions of square feet, probably even millions of square meters, since you're in Europe.
Yeah.
So what is interesting, the roadblocks are basically, how shall I say it? It's a structural problem. It's not a technical problem. Structural because engineers are trained to put in whatever the software tells them, and the software is produced by manufacturers. I'm just telling you a little bit of a background.
Yeah, I'm interested.
Yeah. So what I'm doing, I'm using concrete floors linked with the heating cooling systems. So the buildings become rechargeable. So we can store energy, specifically heating energy or cooling energy. So it's called thermal energy. Now, what usually is being sold is battery storage. Batteries, like Tesla, for example, batteries. And they put, in the United States, they put large containers, 40-feet containers, a lot of them. So they make energy from the sun, they store it in the containers with the batteries, or they use it and the surplus is stored. So a lot of them, millions of dollars are spent. And there is a reason why they're doing it. In a way, it's kind of a good reason, but in a way, it's a fake reason. So what is happening is we replace a lot of mechanical components and parts that no longer necessary. You see, we did buildings in Canada, we did buildings in the United States. They have been rated best performing in a survey of close to 5,000 buildings. So, and the reason why is because the concrete floors, when they act as a rechargeable battery, we can pick up all kind of very low grade energy that right now is kind of being thrown away. We can pick it up. So now when we work in an institutional setting, it means with governments or semi-government, entities. We worked with them in the past, but you have to find a needle in a haystack or the right person that would say, yeah, that's maybe not a bad idea. The problem with engineers then could become, because if they rely on them as experts, they rely on their opinion, but not on the facts. And many engineers don't want to change too much. It's surprisingly, like if, for example, somebody is going to a doctor, a family doctor, they'll tell you go to see a specialist. But in the engineering profession, it doesn't exist. So that's why when the decision makers go to, say, I have to talk to my engineer, and my engineer basically is not always willing to basically work with you because they feel like, another cook in the kitchen. And they don't like two cooks in the kitchen. They say, I'm the cook, I'm the general, I'm in charge. I hope so far it's what I'm explaining is okay.
Yeah, I like the style you have. It seems you practiced a lot to simplify the message.
I practice because, you see, a lot of the decision makers don't know the technical part.
Yeah,
So
and this is
they
what I
have to,
was, trying to
so they
explain.
have to understand in other terms. So in any event, as I said, our buildings in Canada, they are basically listed by the Government Energy Efficiency Office of Canada as best 12 years ago. And in the United States, we did the largest portfolio of buildings that produce more than they consume, and they're listed in the Guide to Zero Energy by the Department of Energy of the United States. And we didn't pay for it or didn't ask for it, but we are there. So what is interesting, that's the good news. The not so good news is we basically find huge resistance from, you see, the decision makers that rely on engineers. And you see, I realized that a lot of engineers, they're like McDonald's. I'm sure you probably have in Romania McDonald's too.
Every country has.
Every country, okay. So you see, they're basically production shops. So they basically don't have time for any innovative solutions like ours because they feel they lose money. And they don't want to be too much involved. Although, we basically, as I said, we've done big buildings, all kinds. We've done small buildings. And we did, residential, custom residential. Custom residential, we didn't kind of wanted to do, but we basically did it because the guys that we worked on large projects said, oh, it works so good, we would like to have it. So we did. So also, we have very good examples of doing that. So to get the message out, we basically kind of, we really have to have a bit of a challenge to re-educate the engineers, which is a huge challenge because they are the advisors to the decision makers. And some of the decision makers, as I said, you can find very few of them that basically say, yeah, that's a good idea, let's try it. And the best part that we guarantee what we do, because many engineers, the first question is who's going to be responsible because they don't want to go to court if, let's say, not enough heating, not enough cooling, or some other problems they may think about. But as I said, we don't. It's actually dials in exactly into what everybody's talking, and why so little it has been done. Main problem: it costs too much to do what they're talking about, and we eliminate a lot of this cost and complexity that is put in the buildings. It's not only about the energy storage, but it's about, you see, the indoor wellness. Like, for example, the floors become warm floors or cool floors. Like they are radiant, like a technical word for it, radiant. But a warm floor, a lot of people understand. Like in a five-star hotel, you find it in the bathroom, warm floors. So when people step out from the shower, they want to step on a warm floor. That's all they have. Our buildings, all of them have warm floors and cool floors. So cool floors practically don't show up on a radar as kind of as a meaningful kind of solution, although it offers much better efficiency. So if people would put in the warm floors and cool floors, first of all, they need a lot more expensive equipment, which we don't, and then they have to maintain it, and we don't have to maintain it. Now, another big thing that basically we're addressing, you see, is the concrete floors. People say that concrete is polluting. It's a dirty material. In our case, it's actually carbon negative. It means because we take out a lot of other mechanical parts that produce that pollution, we don't need them anymore. And not only that, but we don't need to maintain them. That's
Okay.
another thing.
Let me
So
stop you
that
here.
is in short what we're doing.
I want to clarify this part because it's important. You addressed so many aspects. Well, so about the concrete, because this was also on my mind. Okay, it is a polluter material to produce the concrete. What you're saying is that this is your only polluting or the most polluting part, and that eliminates other polluting parts that are in a construction. And if you do the math, afterwards, you are positive. Carbon positive with your buildings.
That's exactly what's happening.
Okay. Okay. But you still keep the concrete, and so this is the fight, one of the fights you have to deal with, because we found a solution, but we still have a polluting part inside our design.
Yeah, but the biggest obstacle, I mean, the biggest part is a lot of the constructions today, they were always had problems going over the budget. It means whatever they want to put in or they want to build, it costs a bit more. And now, if we basically say we have to reduce the pollution, the costs go up to do that because they have to put in additional equipment. In our case, we don't need to do it. So our buildings don't cost much more. Sometimes it's a capital cost saving compared to conventional. And so that's where we basically, kind of sit. You see, for example, talking about one item, like the energy storage. If we're talking about thermal energy storage, it means storing heating or cooling. In this case, for example, cooling. So there are regions where they need a lot of air conditioning. So during the day, when everybody wants the air conditioning, the power stations cannot support everything. So they basically have a problem. So what's happening is they basically, there are guys that make ice at night, ice. And they store it, and then during the day, they don't need mechanical cooling, but they need ventilation to move the cool air across the ice. So, and buildings like that exist in New York, for example. Straight in Manhattan, there are quite a few buildings. They're doing it in warmer climate too, like in Abu Dhabi, in Dubai, and other places. They make ice at night because they basically kind of use the energy that nobody's using at night. So we basically balance the day and nighttime energy, and that's exactly what we're doing. We use a lot of energy at night. We don't need too much energy during the day. And the heating and cooling takes up 75% of the total energy use. So we basically virtually expand the energy supply. So it creates a good positive effect. Now, so we basically, as I said, our message, we have to talk, and then people, have to check with their advisors, and the advisors basically may have their own reasons. Sometimes they're selfish reasons. So that's basically where we are.
Unfortunately, yes, it's part of human nature. That's why we didn't solve the SDGs already. You also have a history, and that means that some of your buildings have many years already to show that they are sustainable and resistant?
Yeah, so we have that history, and you know, it's still kind of, it's a very difficult situation. Yeah, yeah. So that's where you know we are. So,
What do you
I
need?
know. Pardon me?
What do you need?
Well, I guess you see the question is basically, I guess potentially get an exposure that gets a bigger attention, you know, and that's. But we are swimming against the people that supply all kind of equipment. You see, we're upsetting a lot of people.
Yeah.
If
You
we say we
remove,
don't,
if you should choose a percentage of how many things you are removing from a standard construction, what would
and yeah,
that be?
we did, and we removed quite a bit, yeah.
What is 10%, 30%, 50%?
Okay, so you know, actually, from the mechanical setup, we actually remove about 40 to 50, 40 to 50%.
Wow. Wow. Yeah, that's a lot.
Yeah.
Mm-hmm.
So, you know, 10%, everybody's talking, we do 10%, 20%, whatever. But a lot of it, it's not, it's more marketing than in real life. We remove a lot.
And if you would need to paint a beautiful marketing campaign and an image, if a city like New York would implement your solution, or the buildings, they would go net zero and even produce more than they
Yes,
consume.
yes. They would produce more,
And
actually.
this
Not,
could be also connected to the grid, for example, for
yeah.
transportation and utilities.
Okay. Okay, so what's happening? If we have a lot of them, they become energy sharing buildings. So it's not only that they basically, you know, we would need a smaller supply system because we basically, you see, there is a lot of energy available at night because people sleep, don't work, and things like that. The transportation aspect of it, it's predominantly if we charge electrical cars, you know, because if it's gasoline driven, so it has very little to do with us, with
Yeah.
the energy grid. But, you know, so there is a way how to balance it. There is a way how to balance it. So I guess it would be, you know, one part is probably to find some logical partnerships, you know, that basically would like to kind of larger entities that a lot of the larger entities you see, they do these green buildings, but mostly, you know, their payback is free publicity that they get, but not much more. Predominantly, somehow, no matter how much we talk about saving the planet, saving the environment, doing green and this and
Mm-hmm.
that, it boils down to how much does it cost? Because a lot of these green solutions come with a premium price. You know, the first, when you talk green, they basically say, whoa, whoa, how much does it cost? A lot of the decision makers. And then basically they say, does it work? It's too good to be true.
Mm-hmm.
You know, because a lot of people are kind of just the mindset is influenced by the manufacturers so much that they know if you say, oh, it's going to be green, they say, well, we don't have the money to do
Yeah.
it. You know, so it kind of no matter what we do, and that's why you see in the United States they kind of offer all kind of grants, incentives, tax breaks, you know, to do green, but not much happening in percentage.
But people don't even know that, for example, now the solar become cheaper than the traditional ways to generate energy. And the only misunderstanding is just because of the subsidiaries that they still exist and all the facilities that the governments had with oil and gas suppliers.
Yeah, this is a kind of long, interesting. Could be a very long and interesting, discussion how it works, But
But don't you agree? Don't you agree that now I heard many experts talking about that solar panels are becoming a cheaper model, and China is one of the big promoters of this, like going green with this, and as the
yeah.
capacity to
So
production increases, the cost also decrease.
you see what's interesting? This solar panels by itself, it's another kind of mechanically driven event. You see what's happening. There's a lot of free energy that surrounds us. A lot of free energy. For example, in the air conditioning mode, we have nights that are very cool. So we can use a ventilation fan. With 1 unit of power, we can draw in more than 1 unit of cooling. So we don't need solar for that. In Canada, for example, schools are heated with the body heat of the students. The body heat of the students. We don't need heating. With minus 14 Celsius outside, we need zero heating. Minus 14.
How do you connect the body temperature? Because it's known that, okay, if you're in a closed space and you have many people, they will obviously heat the room. But how do you do this in a
Well, this is
systematic
it.
way?
That's what conventional engineers don't do, and that's what we do. So here's the thing. And I'll give you another simple example and simple math. You see, this is researched 100%, and it's in the engineering handbooks documented that men are equal to 100 watt. They call it now Edison light bulb. So it's the first light bulb. Men, 100 watt. Ladies or women are 105. So ladies, you produce 5% more heat. That's how basically it works. I don't know why, but that's what it is. It's measured and documented. It's not my fact. Now, say you have 500 students or 1,000 students. Now you multiply by 100. That's a lot of kilowatts of heat.
Yeah.
A lot of heat. So what's happening is, but not everybody is in the same room. They're spread out throughout the building. So you see, we have supply energy. We need to supply fresh air. It's by requirement. And we have return air. So whatever we bring in, we have to return. So the air that returns is much warmer because the body heat kind of warms it up. So we pick it up and we move it through a ventilated concrete floor. So, and the way we move it, it becomes like an energy exchanger. And the concrete floor is not only storage, but an energy exchanger. And then basically we radiate back into the space. So it's, and it's driven by a computer that kind of balancing all this kind of little minute energy that is in the space.
Let me see if I understood this, because it's so fascinating. It's close to biomimicry. We have tomorrow our show on biomimicry, and I'm so interested in this. So
I can send you a little video. I have a video from the school.
Of course.
We did it's an old video. We designed, actually it was done not for commercial purposes. It was to teach the children in a school, the kind of school that they are in, that they can heat the school with their body heat.
Not all buildings are created equal, and some are created much better. Like your school. Yes, the one you're sitting in now. One that cares about the environment. Did you know the floors and ceilings of your school are made of concrete? Concrete is an amazing material that can act as a rechargeable battery 24 hours a day. It's just like charging your cell phone, iPad, or other electronic device, except that concrete makes use of an abundance of free energy available all around us. On a winter day, your body heat and heat from lighting and computers warms up the concrete inside the school, while outside, the sun heats the building. On a summer night, cold air is captured and stored in the concrete floors and ceilings to be released upon demand when school doors open in order to maintain a comfortable indoor environment. That means your school is at work supercharging itself day and night with free and natural energy to meet the heating and cooling needs for everyone inside it. In scientific terms, this process is called thermal mass. By definition, thermal mass is the ability of a material to capture and store hot and cold temperatures. Concrete is one of the best materials that can be used for thermal mass, which is why it's been chosen to be used for the floors and ceilings of your smart school. How smart is that? Unlike old buildings that rely on non-renewable and polluting materials like coal and petroleum to power heating and cooling equipment, your school is contributing to a healthier planet simply by using concrete in a smart way with thermal mass. Your school is promoting a better future for the planet by making smart choices in how it consumes less energy today. Besides the sun, your school also makes use of excess body heat that you radiate naturally. Did you know that each one of you generates as much heat energy equal to a 100-watt Edison bulb? And in a school of 500 people, that is equal to the energy created by 50 toasters turned on for 8 hours. Your school also captures and stores heat generated by all of the computers and lighting that would otherwise just go to waste. Your school is smart because it can capture and reuse all of this free heat energy. Pretty amazing, isn't it? Think of it as recycling energy. The same way a tin can or piece of paper can be thrown into a blue box to be reused at a later time. Not only is your school smart by saving energy, but it's also a healthy place to be because of its enhanced ventilation system. Fresh air is constantly flowing into your classroom and exhausting it to the outdoors. So when someone sneezes, you don't have to worry about their germs sticking around for a long time. Your school is a great example of how using regular materials like concrete in a smart way can help conserve energy while promoting indoor comfort and health. It just goes to show that doing a few little things can really add up and contribute to the overall improvement of our planet.
If we are in a space where it's very cold and it's winter, and we are 50 people in a large room, and if you are just like this, we warm a little bit, but we are still very, very cold. If we are using your system that is designed in a way that can absorb the heat from the individuals, put it somewhere, bring it in a way, in a circulation, in a way that that kind of heating becomes more efficient and gets back into the atmosphere inside that room and heats the room that otherwise gets lost.
Yeah. So, okay. So basically, that's right. So we supply the energy, and you say we supply, basically we need ventilation. Ventilation is required, fresh air constantly. So then whatever we supply, we have to return, because the building is not a balloon that you can blow so much energy, so much air in, you have to return it.
Sure.
Return whatever that energy, that air supply comes in. So it's kind of in a balance. Now, what is interesting is we, instead of actually throwing it outside, we actually pick up and bring it back through the ventilated floor. I can show you a diagram, actually. I may.
Okay. So you don't let the heat to just get lost outside or in the atmosphere.
Yeah, it basically we
recycle it.
Exactly.
Okay.
Exactly.
Okay, recycle your body heat with us. Okay, very nice.
So I can show you a little bit of a diagram. Okay, so what is interesting is 135 degrees Celsius into, and this is the supply air temperature. So our body is a little higher than the supply air temperature in the buildings. And so it has been tested in a cold climate, hot climate. So you see, reliance on solar, we don't, when we say solar, it's not the magic bullet. It's good to have, but it's not necessarily. We have a lot of energy that we can pick up, free energy that we're not picking it up right now. We're not picking up. And again, you see, the buildings usually work in a 100% mechanical mode. It means you need cooling, we turn on the cooling. You need heating, we turn on the heating. The problem is that we have a lot of heating or cooling naturally that is right there. The other thing is what's happening, because we have so much cooling and heating free, we can afford to introduce more fresh air, and most of the time it's 100% fresh air. What it means is we bring in fresh air and we totally remove the stale air. Today, when they say there is a 100% requirement, that does not mean that you're getting 100% fresh air. 100% requirement means that if you supply only 20% of fresh air, that should be okay. That is kind of a definition problem. And that's why that's in our buildings are 100% fresh most of the year. On extreme days, we may need a little bit of recirculation. You see, we had a medical building. During COVID. They were treating COVID patients. They were open and treating COVID patients. And they didn't have any problems because we didn't recirculate viruses. A lot of people in the United States and Canada, they died because of recirculation.
So you have such a building with such an example from COVID, but this is huge. This is huge.
Well, I know it's huge. Now the question is how to convince the guys that like to do business as usual. They said, well, we were doing it for so long, it was fine. So if it killed a couple people there or more than a couple, it doesn't matter. You see, it's as I said, it's a huge educational challenge. You know what you're doing in the biomimicry, actually, in a certain way, it relates very, very kind of, it dials in exactly in what you're doing. Because
what the termites are doing, right? Because they have that kind of natural ventilation, if you know about termites. And I was fascinated to learn about that.
Yeah, but we're doing it in real life. You see, this is the thing. A lot of people are talking, and a lot of people basically have, been basically influenced by a lot of information that is actually incorrect. Incorrect. When we show up, a lot of engineers, they don't believe it can work. Engineers that, we've been doing it for so long, we know everything. And that as soon as they say we know everything, those are the guys that are the biggest problem.
Yeah. And you also need to connect this with the SDGs, solving our climate problem with your buildings. And this can bring more responsibility on their heads to let go their old ways that are not working.
Yeah, okay. So that brings up another interesting problem. A lot of them are responsible, but never accountable.
Yes. And this happened especially with all of those agreements, starting with Paris Agreement, that, okay, let's just agree on things, but no one is accountable of anything. Tech Leadership Lab is an action-oriented think tank, but it's a lot more. We want to unite the parties. We don't want to reinvent the wheel. We already discovered that there are solutions out there to solve the SDGs sooner, but exactly as you said, we need to speed up our game to let go of our old solutions and start to align for a common good as a humanity. So for this reason, we want to show that today what we need to do is unite and act fast in order to save our future generations and life on Earth, basically. And we are running out of time. And the SDGs, we have 17 SDGs from the UN. But the most urgent one is the climate because it's linked to everything. And so we decided, okay, we will put voices together, but our role is to find the clusters of little TLLs like Tech Leadership Labs that are already doing the job in a way that we unite the voices and decision makers and policymakers and create that kind of pressure that, okay, these are the solutions today. We have the solutions. We just need to connect them to the grid on a global scale fast enough that we can move the needle in order to solve those SDGs sooner, because those 2030 and 2050 goals are already outdated. If 15 years ago, we're just like discussing, we will have a climate issue. Today, we have the climate issue, and we still are just in an agreement phase. And so everything that is about us, it's fast-moving, startup-like, first principle thinking, exponential growth kind of movement, online movement that wants to put these things in front of the decision makers and create the pressure. So we decided that our first global summit online remotely will be around what we think it will be around all the SDGs to be solved: climate, AI, and humanity. Climate because it's the most important SDG and it's directly correlated with what comes. AI because AI can be the solution of finding what we don't see right now, and just put together technology and innovation in a way that it will find ways that what we cannot do today, we will be able to do because AI provides us the solutions and options. And humanity, because we don't need to lose ourselves on the way, and we need to care about each other at a united fashion where location, age, gender, and ethnicity doesn't matter. Because these are decisions that we need to take globally as a global government, and we need to deliver. And so we will also want to work as an entity that unites voices, and because of us, they can connect and talk, and also provide the clear steps that what we can do in order to do the things we discover through our summit and our events, like this first summit in March. The intersection between climate, AI, and humanity has also an initial product at hand, a consensus document, not white paper, not other kind of documents that are too long, too laborious to be understood, but a consensus document about what we identified as being urgent to do first and how, the steps, and be very, very easily marketable and brandable in front of everyone, but especially the decision makers. We want to create that pressure and accountability through our media company that we are also building.